Okay, so thanks for coming again. So this is the second session of the regression part of this course. So this will be the last about specifically regression. So we will spend 1 hour and a half talking a bit more about that. So first to start, okay. Sorry, thought I had this fixed. Okay. So I wanted to talk about the survey, but it seems that only 2 of you remembered to go there. So my advice is just try again. If you want to take the survey, and then we can come up with a few statistics. I guess most of you forgot, so just check again the slide of this week. So last week we've been talking about regression, and what is regression? It's basically the task of highlighting some functional relationship, try to find a good functional relationship between predicted variables and predictors. So you have access to predictors, you want to predict something, and that would be the blue variable. And so to predict, what we assume is that we need to find a good function that goes from the space of predictor variables to the predicted variable. So we assume that there are pairs of such observations in nature. So there is, for instance, I don't know, the scan of a lung of a patient and the information that this patient is ill or not. As we were saying earlier, the information, a lot of information about your health and whether you have a good or bad level of cholesterol, etc., etc. And so we assume that given the first half of the data, we can recover the second half. So recovering here is in very not very clear terms. So we need to make a choice to measure how good we can recover that second half of the story. And what we've been going through was this least squares criterion. And so we formulated the problem as, if you want to find a function, an accurate function f, such that being given only half of the story, you can guess the other half approximately, we formulated this as using a data set that is using pairs of examples that someone has collected in nature, find a function within a function class that you have pre-selected, so this would be this big F, such that this particular choice minimizes this function. And what is exactly this function? Well, it is the difference between what actually happened, was observed in nature, and what you predict. And this difference is brought up to the square to emphasize, to insist on the fact that if there are big errors, then this is bad. If there's a small error, then this is not a big problem. So if you adopt this formalism, this framework, then we saw that if you want to regress a real number versus a real number, that is, your observations x are just one number and y is one number. So we took the example of the surface in an apartment versus its rent. This is just very simple regression of one variable versus the other. And if you use the least squares criterion and b, a1 to ap are the variables that you need to select to choose your function, then since the criterion is a second order function, because it's a least squares, it's a squared function of, it's a second order polynomial of every of your parameters here, then if you want to find the minimum, you have to find a point which satisfies what is called the first order conditions, which means basically the derivative is 0. And in that case, when you derivate a function of the second order with respect to the parameters, with respect to any of those parameters, here just AP for instance, it becomes a linear function in those parameters. So basically you are left solving a bunch of linear equations equal 0, and this is a linear system. And so we get, if for instance we assume that the function is polynomial of order p, we get p plus 1 linear equations for p plus 1 variables. And each of those variables are the coefficients of the polynomials. We did something very similar, but in a slightly different setting, which is that now we assume that we have one real number that we want to regress versus d real numbers. Basically, our observations x are vectors, and our predicted variable, the one we want to predict, is the number y. Then I'm walking through again very briefly the computations that we did last week. We said that if we want to find the best vector alpha and the best such that, and the constant alpha 0, such that alpha transpose of x plus this constant alpha 0 is not too far from y, then it's the same idea. We build up a big matrix of data, which is basically of one dimension d. Each observation is just one column vector. So we usually call the number of observations big N, okay? And then we just write, we add this row vector of ones to form what we call the data matrix, which is a matrix which has d plus 1 lines, so the d that we had in the beginning and this one, times n columns, okay? And then finding a vector alpha, so we add to the data matrix a row of ones to get the predictors x. The row x of predicted values is this vector of, is this vector y, which holds the actual value for any of those examples. Then finding a good vector alpha, which will be such that alpha transpose x plus alpha 0 is not too far from y, is basically, and using the least square criterion to select alpha, is equivalent to forming this function L of alpha, which is just simply the Euclidean norm of the vector y minus alpha transpose x. And if you expand this function, you get this. And we saw in the last lecture that basically when you take the gradient of this function with respect to alpha, and you want it to be 0, which is the first order condition for the minimization, then you obtain this relationship. Okay? So alpha, the vector of weights which tells you which variables are important depending on the value of, so you remember we were talking about the rent versus the surface distance and age. This vector alpha is actually computed directly through this formula. Okay? So there is one thing that you have to notice though, which is that this formula is also, it only holds if this matrix here is invertible. This is just a standard prerequisite of taking this formula. So we briefly mentioned this when this might appear at the end of the lecture. But if we just put this problem aside, when we have this task, if I give you on the one hand the vector of rent, and I give you the data matrix, which is the, for each variable we have a lot of observations, then if I just directly put this into MATLAB, so x here is this matrix plus a row vector of ones here at the top. If I just, or at the bottom, sorry, here it's at the bottom. If I just type this, x prime slash x y prime, so this is the same notation as taking the inverse. It's just numerically more stable. Then this is the answer that I get. And what does that answer give me? It gives me the coefficient for each variable. So here we had that the rent of an apartment can be guessed based on the age, surface, and distance by following this equation. The baseline is 27,000 yen minus 0 point something times the distance. So basically, the bigger the distance, the lower the rent. This agrees with intuition. Surface, for each additional square meter, you would have to pay 0.16 times 10,000 yens, so 1,600 yens. And the age is also a depreciation factor. The bigger the age, the cheaper the rent. So today what we will be covering is a few topics which each could be the subject of one lecture on its own, but I would since we're a bit, we only have 7 lectures here, we will go quite fast. But if you have any questions on those topics, you're of course free to ask them after the lecture. So we will first start with the statistical probabilistic perspective on least squares. So far, I haven't really motivated this choice. The least squares approach was not motivated other than by a computational reason. I told you that it's easy. If you use least squares to penalize the errors, then you get either simple linear systems here or linear system here as well. So is there another motivation? And I will try to show this one. Since it was part of the first assignment, I will just tell you why it's a problem to run regression with polynomials in higher dimensions. I will emphasize a geometric perspective on regression. That is, when we do this, when we try to find an alpha, which minimizes this, what are we doing? Can we have a geometric intuition? And when this can work? And then we will close the lecture with some words about overfitting. And this will introduce the lectures on statistical learning theory, which will come in 2 weeks. And I will talk about some advanced regression techniques to avoid overfitting. So let me just go quickly, go to very few words on the statistical probabilistic interpretation of least squares. So far I've been telling you that I assume that someone has collected pairs x and y in nature, maybe 10,000 of them, and then gives them to you. And you have a big data set. And then if you take the least squares approach, then you can compute an alpha or something. Now let's take a slightly more involved, make a more involved statement and assume that actually in nature there is a law that governs the apparition of x and y's, a probabilistic law. And the probabilistic law is the following. There exists a vector alpha and a constant beta. So the vector alpha is of the dimension of the variables, so it's Rd, and beta is just one value. So we have Rd, R1, so it's Rd plus 1 if you want. So there is d plus 1 parameters, such that I assume that these observations here, x and y, are such that if I take y minus alpha transpose x plus beta, then this difference here follows the normal distribution. So what is the intuition? Well, it's basically, it's the following. In nature, well, a very strong statement would be to say, in nature, if I have x, then necessarily y is equal to A transpose x plus beta. So this is a deterministic relationship. Okay? So if I have, for instance, this height, this weight, this I don't know, circumference here, this blood pressure, etc., then for sure my cholesterol level is 122, for instance. So since this is a bit, I mean, it's difficult to believe because we know that there is a lot of randomness at stake that comes either from measurements or even just because everyone is not the same, then we assume that a slightly less strong belief, which is that we believe that actually y is usually very close to alpha transpose x plus beta. So if you give me x, actually y is very close to alpha transpose x plus beta. But very close in which terms can I formulate this? Well, the difference between both is going to be distributed as a normal density with variance sigma. So what is the mean of this normal density, centered normal density variance sigma? It's 0. Okay? This means that on average, y minus alpha transpose x plus beta will be equal to 0. But that's just on average. Most people will not be such that y minus alpha transpose x plus b is equal to 0. Okay? So is there some question here? Is there something that's not clear? Okay? So this is the statistician's viewpoint. To model, to write that there is a model out there for our observations x and y's, and the way that x, the first half of the story, interacts with the second half of the story, x and y, is through this equation. And this is a probabilistic relationship, right? It just says that the residues, so this quantity here is often called this is called a residue. Okay? And I think the most important thing that we have to understand is that the residue we assume is 0 on average. Okay? Because if this residue was not 0 on average, if the average of epsilon was not 0, then it would make sense to put it into beta. Okay? And then the other thing that we assume that is important on this residue is that it's normally distributed. So you know the normal density. Basically, most of its weight is around 0, and then it decreases with thin tails up to infinity. So it's very unlikely that this residue is big or not. So this is the assumption that we make, okay? So, of course, this can be rewritten as y in nature will always be equal to alpha transpose x plus beta plus a fudge factor, if you want, something that just changes things a bit. And I assume that this epsilon, this noise, sometimes it's called noise, but I think noise doesn't really reflect the fact that it's not just about measurement noise. It's also that basically nature is not deterministic. So there is something that appears here, and this is distributed this way. So if you start from this assumption, the goal as a statistician, at least as a frequentist statistician, is to try to guess alpha and beta using data. Okay? So it's slightly a different, I'd say it's a better motivated approach. In the previous approach, in the previous lecture, I just said, okay, let's take least squares. This is a good quantification of how good or bad my function is and minimize it. I would say it was a pretty blunt, direct, not very motivated approach. But here I'm saying, okay, this is my assumption. This is what I think happens. So now I want to estimate alpha and beta. There's not much you can say about this, right? It's a better, the fundamentals are better motivated. So now that you think this, let's estimate alpha and beta. So what is a technique which is used throughout the statistics to estimate parameters? Well, it's called maximum likelihood estimation. So let me just walk you through those steps. So we assume that the parameters, let's make the hypothesis that, well, I don't know alpha and I don't know beta, but let's assume for a second that they were actually generated with one value A and one value B that I know. Let's say A is equal to, let's say, 0.13, 0.15, and minus 3.5. And B is equal to 1.85. Okay? So let's assume also that those are the values that generated the data. In such a case, if I assume that the values alpha and beta are A and B, what is the probability that each observation that I see that someone gave me appears? Okay, this is a bit subtle. Well, the probability, as you know it, is that if you know the parameters, if you know that alpha is actually A and beta is equal to B, well, you know, remember that we assume that the residues, epsilon j here is the residue of one, epsilon j is the residue of one particular observation which I have been given, and I assume that this is actually what happened, alpha is equal to A and beta is equal to B, then in that case, if epsilon j is this residue, I know that it has a normal density. Okay? So the probability that y and j appear if a and b were the ones that were responsible for the relationship between y and xj, sorry, yj and xj, then it's just this. This is just the Gaussian density, right? Okay? So the probability of seeing xj and yj, this couple, assuming that alpha is equal to a and beta is equal to b, and I should probably also say sigma is equal to sigma. Well, let's assume that sigma is known. It's this, right? And now let's go to another very important assumption here as a statistician, which is that I assume that you gave me a sample of data which was independently sampled. Okay? So if you have a background in probabilities, you understand what this means. If you don't, let's just assume, for instance, that we have this problem of trying to, okay, let's take the rent problem. I want to estimate the rent with respect to surface, age, and distance to the station. Assume that I want to estimate this relationship in Kyoto, in the whole of central Kyoto. And I'm a real estate company. And I ask one of my employees, can you just go and sample prices and all that information for apartments? If you go and only sample that information in one very specific area of Kyoto, then there's no hope that this sample will be helpful to find a formula for the whole area of central Kyoto. So if for instance, in my, I showed you some analysis, regression analysis with respect to apartments around Kyoto University. If I had narrowed down my search to only apartments in around Hyakumanben, for instance, or let's say something worse. Imagine that I just narrow my search, I just check for apartments which are exactly within 2 minutes of Demachi Yanagi station, okay? Then the information of the distance to the station is completely irrelevant, right? Because all of the apartments will have roughly the same distance to the station, and this will derail completely my analysis. So the idea of independently sampling data is that it has to agree somehow with your hypothesis. If you're trying to model apartments in central Kyoto, then you expect to sample equally from apartments in the whole of central Kyoto. Okay? So there's lots of ways of interpreting the independence property assumption, but here I'll just stay with this one. Suppose that we have this, we have reached a good sample of apartments. Then what you can do if you know that that sample is in IID, identically independently distributed, then you know that the probability of all that database actually only depends on the probability of each individual measurement. Meaning the probability of seeing such a sample of points is just the product of the probabilities of each individual point. Okay? So this is the other assumption that a statistician needs to make in this case. The data is generated with a linear model, alpha and beta, and the data is independent. So this is the probability. So typically, what would you, for instance, suppose that the data was really generated by a value of alpha and beta somewhere, and then your value, the values that you have chosen, A and B, are completely different, are very, very different from the actual value. So for instance, imagine that you're very stubborn and you think that an apartment's rent decreases fast with respect to the surface. So let's take again the example. Surface, distance, and age. Suppose that your guess is that with respect to the surface, the coefficient is minus 0.2, meaning for each supplementary square meter that you add, you have to remove 2,000 yens to the rent. Something stupid as well as plus 0.1 times the distance. For every minute more that you have to walk to the station, you have to pay 1,000 yen more. And age would be, let's say, plus 0.2. For every additional year of the building, you have to pay 2,000 yen more. Okay? So this is completely stupid, right? And then let's put B. The value of B, let's put it at, I don't know, 40,000 yen. Okay? Then what would you expect this probability to be here? Okay? You have to imagine. You believe that the relationship between the rent and those variables is the following, and you're a really hard believer of that. And then you observe xj and yj's. Basically, most of your yj's and xj's, I mean, most of your predictions of yj given xj will be completely wrong. So basically, if this is wrong, if this is very far from this will be very big, and this will be very small. And so the probability of the sample under these assumptions here is ridiculously small. Okay? So this is the intuition that drives the likelihood. The likelihood of the data set as a function of A and B is exactly this probability. It's what is the probability this data set had been drawn if the actual values were A and B. Okay? So you see A and B as parameters here, and the maximum likelihood approach is just simply the idea of taking the parameters A and B which maximize this quantity. So maximum likelihood approach is basically to use this criterion, the likelihood, as the way to select A and B. Okay? And what happens if you do that? If you maximize this function here, well, I think you will agree that if you maximize a function, then it's the same thing as maximizing its logarithm, okay? Because the logarithm is an increasing function, monotonic increasing function. So it's the same thing as maximizing L or log of L. And of course, if you just take log of L, you have a constant that appears there, but it's just a constant that depends on the number of points. And then you have this quantity. Because if you take the log of this product, then you have the sum of the logs, and then you have the sum of log of exponential. So then you have simply just the sum of minus this. So if you maximize this, of course, maximizing minus this is the same thing as minimizing this. Okay? Maximizing a function is the same thing as minimizing minus the function. Okay? So what do you get? Maximizing the likelihood is the same thing as minimizing the orthogonal, the least squares criterion. Okay? So this is just a very, very quick explanation. The statistical approach gives you a lot more ways to interpret your results than the real, just the idea that let's minimize these squares. So this is why it's interesting. You can prove a lot of results on, if you have a lot of points, usually you can get a better estimate of your vector alpha. You can also get confidence intervals for the coefficients. And you can also use test procedures to assess if the model fits the data. So here is the interesting thing. I have assumed that the residues each year are follow a normal density. Once I have computed A and B, is it true that the residues that I have found in the data actually follow a normal density? So here is, for instance, the example, in the example of the rand and surface, etc. This is a plot of the residues. Okay? So I should probably switch a bit to MATLAB to show you a bit. So let's load the data. And I should have it. OK, so this is the first plot. Reshuffle entries. Plot the matrix using rent in thousands of yens. So this is what you know, you've seen quite a few times. So this is what we were doing yesterday. I'll just do it again for the sake of doing it. This was, if you were to minimize just, well, I don't need to detail this because you can do it. So I'm just going through all the computations. Okay. And then here at some point, okay, this is where I remove the outliers. These are the new coefficients. This is the coefficients that we had last time. So this is when you don't remove the outliers. Remember that we had a discussion that if you just apply directly the formula to all the points, then you have a problem. If you remove the outliers, you get this equation. And then here should come what I wanted to show you. So this is where it really becomes important. So remember I told you that the residues are actually what you have left once you remove from the actual observation your prediction. Okay? So here I'm just doing exactly that. I'm taking y, the observations for y, minus the prediction. And the prediction, remember, is x times transpose alpha, and alpha is this vector. So this is my vector of residues. Okay? Those are the values of my residues. So now let's just simply plot the histogram of those residues. And I have plotted the shape of the Gaussian density. I've superimposed it there. So does it sound reasonable to think that those residues are normally distributed? More or less. I don't have a very good answer here. But intuitively, you can see that by checking your assumptions, by looking at the residues and the shape of the residues, with what they should look if really you were true, makes sense. So this is where you can do hypothesis testing. Okay? So we will not go through this, but this is just to emphasize that there are nice tools. And then there are also even nicer tools, I think, which are built upon Bayesian approaches. But if you're interested in this, just follow this link here. It will take you to Bayesian linear regression. So that was it for the statistics and the probabilistic perspective on regression. So very few words on polynomials in higher dimensions. If you remember that that was the last question of the first assignment that I gave you. So imagine that you have d variables. That is, you have points x in Rd. And you want to run something that's not just a linear regression, that is not just a linear term times the surface plus a linear term times the distance plus a linear term times the age to predict, but you also want, for instance, to include in your analysis the squared of the surface, the squared of the distance, the product of the surface and the distance, the product of the distance times the age. Maybe those are interesting and relevant variables. So if you consider polynomials up to degree p, which cover all those variables, then you have to consider the space of monomials x to the power u, where this is a generalized notation, whereby x to the power u, when u is just a vector of integers, I mean the product of xi ui, for I equals 1. Sorry, to d. Okay. So with a vector u of weights and a vector xu, you have basically all the possible combinations of variables. What is the problem if you do that? If you add in your analysis a higher order polynomial regression with d variables? Well, the problem is you have a lot of monomials here. And if you just check what this would like for 20 dimensions in p equals 5, polynomials of degree 5, then you have more than 50,000 variables. Okay. So we are in a case where you can form a data matrix which you'll have to start with more than 50,000 variables. And then you still have the same number of observations, right? So here you will have, for instance, let's say age, distance squared times age times surface. So this is a monomial of degree 4. Then age squared times surface, etc., etc. Okay? So you see that you can run into a lot of, a computational problem, because if you have that many variables and you still have, let's say, 300 points or 500 points, then it's going to be difficult to do a regression. So that's usually the first obstacle for a polynomial regression of higher order, and this is somehow the curse of dimensionality. But actually it's doable if you just limit yourself, for instance, to quadratic, maybe polynomials. So you could run this regression with surface, distance, and age by taking a product of the variables, and that would be still tractable. So let me move on to another approach, which is the geometric perspective. So it's also a nice one to keep in mind when you do regression. And it can help you, I think, understand better what's at stake there. So remember that we have this data matrix, x1, xn. Each of those vectors here is of dimension d. So is there any question on what I've been talking so far? If you have any question on either this or this, it's a good time. Okay. So the data matrix, x1 to xn, and the row of ones. The predicted variable, the variable you want to predict, y, yn to yn. So remember that what we're doing is we have here 1, x1, xn. We are looking for alpha. So we write usually alpha 0, alpha 1, alpha d, such that this product will kind of agree with our matrix Y. Okay? I insist again. So this is alpha transpose x is more or less equal to y. So let's just transpose this. X transpose alpha is more or less equal to y transpose. Okay? So what do I have now? I have a matrix. So unlike the previous situation where the columns were each observation, I have a situation where the columns are each variable. Okay? So this will be the surface across all my sample, the distance across all my sample, the age across all my sample. And what I'm writing here is that I want, so here it's not exactly equal that I want, but I want this to be, I want the product of those columns. So if you were in Sanjeev Arora's talk yesterday, you will, he had a slide about this actually. So you're trying to look for a good set of weights, alpha 0 to alpha d, such that alpha 0 times this column vector plus alpha 1 times this column vector plus etc. Alpha d times this column vector, you're just multiplying each column by a scalar, a number, is not too far from y1, yn. Okay? That's the game. That's what's at stake here. You want to find an alpha such that the combinations of those columns is not too different from this column vector. So I don't know if it's a good idea, but here I'm just switching notations. I think it's a good idea because otherwise it will be a bit problematic to carry on with all those transpose. So this is a boldface y and boldface x, and I'm just writing y boldface is equal to y transpose and x boldface is equal to x transpose. So basically this is the matrix boldface x, boldface y. And then I write xk for the k plus 1th column of x. So this is I'm sorry for this slightly misleading notation, but it's because I want to call this x0, because this is just the vector of ones. It's the constant vector. And then there are dxk's, which makes sense, which are each variables from 1 to d. So if you just rewrite this sum here, what you want is to have a relationship such that the sum of k equals 0 to d of alpha k xk is not too far from y. Okay? So this is just basic linear algebra. If you remember, what we're trying to do is just simply rewrite a vector as a sum of other vectors. So when can that happen? So the goal of trying to find this is basically to approximate or reconstruct y in Rn using those variables column vectors. So when is this possible? This is just a very simple linear algebra statement. Can I find an exact relationship between that will give me those alphas? Can I reconstruct exactly y using x0, x1, and xd? So basically, this question is very simple in algebra. It just depends on whether y belongs to the linear span of x0, x1, xd. Does y belong to the vector space generated by those column vectors? So remember that y is this predicted variable across all observations, and the others are predictor variable. So what we're asking is the predicted variable in the linear span of the predictor variables. So suppose this is just a schematic, of course, drawing. Suppose y is somewhere here. Suppose x0, the constant vector, is here. And suppose that x1, x2 are somehow collinear to x0. Then it's going to be difficult to approximate y with x0, x1, x2. In fact, it's going to be impossible to reconstruct it exactly. What we can do, though, is take the projection of this y onto that space. That's the best thing we can do to get the values of alpha. So let's just consider a slightly less pathological case. Suppose x0 is here, x1 is here, and x2 is here. Okay? Each x here is a variable. So I have 3 variables. One is the constant variable, and then 2 other variables. And somehow, those 3 variables span this vector space. Is y inside that vector space? Not. It's not. Still not there. But we can probably consider something that approximates y using what we have here. Now suppose x0, x1, and x2 are linearly independent. So basically, this is the span, and y needs to be in that span, right? So I can find exactly an alpha 0, alpha 1, alpha 2, which will reconstruct exactly y. Okay? So this is the problem that's at stake when I want to approximate y, the predicted variable, using a linear combination of predictor variables, geometrically speaking. So the thing that will be probably the most important here is the size of this linear span. Is it 1? Is it 2? Is it 3? Of course, if I have 100 variables, it could be up to 100, right? So the dimension of that space is the rank space of X. Okay, remember that this bold X is this big matrix where each column is a variable. So the rank of that matrix, bold X, is important. So what we know is that the rank of X is smaller than either the dimension of the number of lines or the number of columns. That's for sure. So what happens? What can happen? What can happen and what can go wrong or can go well? Suppose that the rank of x is smaller than n. Okay? So the d plus 1 columns, so let me just this is all you need to know actually to understand what happens in regression and why it can go wrong. So I have my big matrix X, and then I forgot whether it's probably x1, I guess it's probably, my notation is probably x11, x12. Did I take this? Okay, anyway. I guess it's probably the opposite. I might have made a mistake here. X and 1, etc. and x 1 d x and d. I'm repeating this over and over again. Here there is, well, I don't know exactly what my notations are here, but I think they're probably not consistent with my first notation. So we have d plus 1 column vectors, and they live in Rn. Well, of course, if you have less vectors than the dimension, then you can never have a rank which is full rank. Okay? If I have, let's say, 10 variables and 1,000 observations, then those 10 column vectors will never span R1000, right? So in that case, there is no exact solution alpha transpose x equals y in the general case. We are basically, if you want, we are in this case. Okay? Remember that each of those vectors has actually dimension in a number of points, and there's as many as I have variables. Usually I have, well, when it's regression is well posed, I have less variables than observations. And so the vector y of predicted values will never be in that span. So what you do in that case is that since there's no real solution, accurate solution here, exact solution, you take an approximation. We'll see this in the next slide. But this is the first, actually, condition which really matters. Is the rank of my variables smaller than n? Is the rank of my variables exactly equal to n? And if I have too many variables, then actually in that case it's a pathological case. There is an infinite number of solutions to alpha transpose x equals y. So I didn't write it here, but suppose that I have a fourth vector here. I have a fourth variable. Okay? Then you can write y as infinitely many different combinations of x0, x1, and x2, x0, x2, and x3, etc., etc. Basically, the system is not linearly independent, and so we know that there is not a unique way of writing y, and actually there's an infinite one, number of ways. So this is a problem. Suppose now in this case, and this is really rare, I've just put it here for the sake of completeness, but this never happens. Suppose the rank of x is equal to n, and actually you have exactly d plus 1 equals n variables. So I have 1,000 observations, 999 variables plus 1, that's the constant. And then there's only one solution that you can have, which is basically x minus 1y. But this never happens. Okay? Usually it's really rare that someone tells you, okay, I have 100 variables, and I've picked 101 observations. The rank of my variables is exactly the rank of the size of my observations. Okay, there's only one alpha that works, and that's it. And this is not really robust, because as soon as someone adds a new observation, then this analysis doesn't hold. So the only two cases which really happen are this one and this one. It's either there is no solution, or there is an infinite number of solutions for alpha. Okay? This is really important. So as a paradox, the case where there's no solution is actually the one that's easier to solve. Because if there's no exact solution, well, what we try to do is select the projection. So we say, if there's no solution alpha transpose x equals y, or x alpha equals y, then what we do is we just take the value y hat, which is in the linear span of my variables, meaning I'm taking the minimal point u in the span, which minimizes the distance of y to this. This is just the projection. This is the definition of the projection. What happens if you know a bit about projections? Well, first, this is an exercise. I will tell you later how you have to. You can send it to me by email, but I'll tell you at the end of the course. This is just a small lemma that I want you to prove. If you have a family of vectors which is a linearly independent family, then prove that x transpose x is invertible. Okay? So if we assume this, well, it's just very basic linear algebra. Computing the projection of a point onto a span, a linear span of a few vectors, is easy. So this is just a Wikipedia link if you want to follow it. If I want to compute the projection omega hat of a point omega on a subspace V, then the only thing that I need to do is apply this formula. This is a projector. This is an operator, linear operator, which is a projector. If I put in x my linearly independent family, then the projection of y onto this span is just x transpose x minus 1 x transpose. So why did I need this? Why do I need this? Because I need to show that this is invertible if this is a linearly independent family. And this is sufficient if you want to get this projector well defined. And then I just use this. Incidentally, this projector also gives us the alpha. Why? Because if you just write alpha for this part of the equation, then you have y hat is equal to x times alpha. Alpha or alpha hat, it's just the same thing. I'm sorry, this is an approximation. Okay, so if you remember the first slides of the lecture, you will recognize instantly the matrix that we had before. So this is not a bold x, so it's just it's x transpose x y transpose. Okay. And this is exactly the alpha that we got with the least squares. Okay. Here, this is a bold x. In the previous equation, it was just a simple x and y's. So the alpha that we got from just writing down the equations, least squares, writing the gradient, etc., we could have had it in the very same way using this geometric argument. We're trying to minimize the distance of y to the vector space spanned by the variables. This is just a projection. If you want to check what a projection is, you can, but ultimately a projector is this. If you want to project to the vectors linear span of a family of vectors, you only need to compute this. And this gives us alpha, and alpha is the one that we had before. Okay? So there is a geometric interpretation to linear regression. It's just what is the set of variables which can help me reconstruct accurately the predicted variable. Okay? What is the set of weights? Sorry, what are the weights which can help me reconstruct the predicted variable? So what can go wrong? So as I was saying, if X transpose X is invertible, then we have this directly. If X transpose X is not invertible, it's usually because the vectors are not linearly independent. And there are a few pathological cases that I can show you. But let me just, so if it's not invertible, it's bad, of course, because you cannot apply a formula. But sometimes it can be even more problematic if X transpose X condition number is very high. So let me just show you how this could go wrong in practice. So let's take again the example of the real estate. So I don't know if you've experienced this by yourself, but if you look for an apartment in Japan, sometimes the surface is given in square meters, or sometimes it's given in jo, like in tatami mats. Okay, and so after a few times where you just get used to this new unit, you can easily see that they're pretty much equivalent. But suppose that someone actually gives you the data set and gives you the surface in square meters and also the surface in jo, okay, in your data set. So someone will not only give you, for this apartment, 16 square meters, he will also tell you that it's like hachijo or something like that. And of course, because of some rounding differences, sometimes you might have a slightly different measurement which do not exactly correspond. If the surface is 16 square meters, maybe the person will not give you exactly, I don't know, 9.325 jo, which will be the exact value. It will just give you 9 or 10. Okay, so let's do this artificially. Here H is my table, and suppose that I'm adding to the table a fifth row, which is just simply a fourth variable, and here is the following. So I think that 1 jo is 1.4 square meters, roughly. So if you give me the area in square meters, if I divide it by 1.4, I will get the surface in jo. Okay? And now suppose that there is some noise, someone is not really sure about the jo measurements, and I'm just adding some random Gaussian noise actually here. So the round n is just Gaussian noise. So I'm just creating the measurement in tatami mat. So someone wanted to help you and added in the database a surface in tatami mats. So as you will see, it's actually a disaster if someone does that. So now let's form the matrix which is now my data matrix. So let's put images C of X. Okay, that's fine. So in my X here, unlike my notation here, I put ones here at the bottom, not at the top. And then I've just asked to create another column, which is, I think, which one was it? I just say H is 135. Okay, so basically, this is the measurement in square meters, and this should be the measurement in jo, I think. So they're pretty much the same. So now let's run regression, okay, with our, now I think you're very familiar with this. So the inverse of x prime times xy prime. Okay, so the analysis is pretty similar to the one that we had before. We have 2.7 that comes up as a constant. That means 27,000. This, I think, is probably still with respect to the age, 500 yens less of rent per year. But then things start to get a bit more blurry here, because this was the surface, and the surface comes up with a minus here. And then if you look at the variables for the square meters and the joule, they come up with very, very strong influence. 11 and 15, okay? So those two measurements now completely dwarf the influence of the age and the surface. Why is that? Well, one reason is that if you call the condition number of this matrix, then you have 2 to the power 2 times 10 to the power 9. And maybe it's somewhere up there. Let's see if it's somewhere up there. I think I had outputted the condition number. The condition number before was 3 times 10 to the power 4. So remember that this is the ratio of the smallest eigenvalue to the largest eigenvalue. Sorry, the opposite. The largest eigenvalue to the smallest eigenvalue. So here it went from 3 to the power 10 to the power 4, so basically 30,000, to a value in the power 10 to the power 9. And let me just show you why this condition number has a huge influence. Suppose that I'm just removing one observation. Okay? I'm just going to remove one observation from my database. I remove the last one, actually. I remove the last column. And I remove the last column both for my predictor and for the predicted variable. So now, if I just do that, let me just run again the regression. And what I wanted to show is that this was going to change things a lot, but it doesn't seem to have worked. So let me just do this again with 4 variables. No, actually it's quite stable, I'm sorry. I forgot to double check this one. So usually what you would expect is that if probably maybe removing a variable is not the right idea, maybe probably adding removing an observation is not the right idea. If you would add another observation, then you would have a big variation in those coefficients. And why is that? Well, because the intuition is that alpha is equal to x transpose minus 1, x y transpose. And this here is a matrix which you can write as P transpose times the diagonal matrix. This is the diagonalization. And if you have a very large condition number, it means that the ratio between the largest eigenvalue and the smallest eigenvalue is huge. Basically meaning that the largest eigenvalue, the minimal eigenvalue, when you will invert it, will have a very big influence on the value of alpha. So I'm sorry, this is not really very convincing based on this experiment. But let me just follow up on. Let me just continue to the next problem. The next case, suppose now that we are in the opposite case, where the rank of x is equal to n, and the number of variables is bigger than n. If you remember, I told you this might happen in some settings. You have a lot of variables and not enough points. Well, in that case, you have, this is called a high dimensional low sample setting, or ultra high dimensional setting. Well, in that case, there is a problem which is the complete opposite. It's not that there is no point, your point y is not in the linear span. It's the opposite case, where actually your point y is in the linear span, and those points here, since the number of columns is bigger than the number of points, you have too many variables, then in that case there is an infinite number of vectors alpha, such that x alpha is equal to y. So I should erase this example and really write it more like this. You have a few observations. You have a lot of vectors. And of course, if this set of vectors span Rn, then there exists a lot of subsets of size n of linearly independent vectors. And so you can write y as an infinite number of ways. You can write exactly y as a linear combination of some of those vectors in an infinite number of ways. So in that case, what do we have to, what's the problem? The problem is the opposite. We have to choose what would be a good alpha within that set of alphas. So this can happen, as I was saying, in some settings. I will see this in the, we will talk about this at the end of the lecture. And so to solve for this, you can use something called regularization. So let me just carry on with the final topics of this lecture, collinearity and overfitting. So this, just to follow up with the previous slide, there are some settings where you will have a lot of features and few observations. So for instance, this is the DNA chip. Imagine you have to regress one variable with respect to the activity of or the expression of thousands of genes. Another very simple task is, imagine I receive emails every day on my mailbox, and I represent each email as a bag of words, meaning I just represent it as the number of times each word in a dictionary appear. So if an email is such that the word please appears twice, send appears once, and money appears twice, maybe that could give a hint that it's a spam mail, right? If, on the contrary, these words do not appear, an assignment appears once or twice, maybe it's a mail that you sent me. So another way of visualizing a bag of words is through those clouds, tags of clouds, and clouds of tags, sorry. So basically, the size of each word would be proportional to the frequency of that word. Okay? So using that representation, you could try to learn a regression function which will learn the probability that an email is spam based on all of this. But in this case as well, as you can see, the number of variables is huge here, because the number of words which can potentially appear in email are basically the size of a dictionary. So maybe it's 50,000 words. So here we are another setting where we have a high dimensional problem. And so actually I just gave you the example for this. Another example of this kind of setting is when you run a real estate agency and you collect a lot of variables, a few hundreds of them, and then some of them might be correlated. So you have so many variables actually that they might be correlated. And then you can run into the kind of problem that I just showed in my MATLAB demo. So this all goes to the problem is related to the problem of overfitting. And let me show you why actually this least square approach is ill-defined. It's a problem actually. It doesn't solve our problem. So here is I think the most important observation you can make at the end of this lecture. Suppose we are given d variables. Okay, you have this real estate agency, someone gives you d variables, including the constant variable. Consider the least squares criterion. So what we're trying to do with the least squares criterion is we minimize this function with d variables, alpha 1, alpha d, which are the weights, and we try to reconstruct y using those d variables. Okay? the way we select alpha is by taking the values alpha 1 to alpha d, which minimize this quantity, right? Now, suppose that someone gives you a new variable. You're hesitating a bit. Should I include it in my analysis? Well, if you include it in your analysis, then you will consider the same criterion, except that instead of having d variables, you will have d plus one of them. And instead of only optimizing with respect to those d coefficients, you will optimize with respect to all of d coefficients and an additional one, alpha d plus 1. And then this is pretty much the same quantity, except that you are adding yourself the flexibility to use this variable here. So here's an interesting phenomenon. Well, you could have predicted it easily, but you have to notice it. The minimum, when you take alpha in Rd plus 1, that is, when you take this setting, when you consider d plus 1 variable, this minimum will always be smaller than this minimum, the one where you just consider d variables. Okay? So if you're guided exclusively by the idea to make this small, L small, this least square criterion small, then you have a strong interest in adding variables. Okay? So why is this? Well, it's very easy to see why. Well, it's easy to see why because this here is just simply this where I have added a 0 to the last variable, right? If I just say that the alpha d plus 1 here is 0, then this disappears. This is equal to 0. And so those two are the same. So implicitly, if I'm adding a variable, I'm just adding myself the freedom to giggle, to play a bit with this variable. If I don't allow this freedom, then I just put a 0 here. Okay? So if I minimize with respect to d, it's as if I was minimizing with respect to d plus 1, but setting alpha to be 0. So if I have the freedom to actually play with this value, then I can only make it lower. Okay? So this sum, the least squares, or the residual sum of squares, goes down, has to go down if I add a variable. It will always go down. So the question is it worth it? Is it relevant to add a variable? And this is when we need something more than just least squares. And the thing more than least squares is basically an idea of regularization, or people also formulate it as the idea of Occam's razor. Basically, minimizing least squares only is not clever enough because it will always push us towards adding more variables. So there is a tendency for us to add variables to reduce the least square error. But on the other hand, there is something that has to fight it. And this is Occam's razor, or the law of parsimony. It's basically, this is one sentence, is that one should always opt for an explanation in terms of the fewest possible causes, factors, or variables. So these are two contradictions. On the one hand, we know that if we add variables, the least squares error reduces, so we can reconstruct better the predicted variable. But on the other hand, there is another force here that's pushing towards the other opposite, which is that it doesn't always make sense to have 1,000 variables to explain one other variable. It's better to only have 5 maybe, or 10, or 20. And this is Occam's razor. So actually, I want to show you an example of why this is really, really important. So let's go back to the original regression problem. So I'm just taking here my database, and I'm adding the constant vector, and I'm plotting the residuals. Okay? Okay? So X is my database, Y is the regressor. The residuals, if you remember, is just the difference between the real values and my prediction. Here I've recomputed the predictions using this formula. Okay, I'm just recomputing it directly. And then I just take what I've called in the last slide the residual sum of squares, which is just my criterion, the least squares criterion. It's just the sum of those residuals to the square. Okay, and this is my L, if you want. This is my L of alpha. This is what I've been trying to minimize. Now, this is what I can do. This is the total sum of errors that I make on my database using alpha as the weight vector. So now suppose that someone adds a variable, and this variable actually is just pure noise. It's completely unrelated to the natural phenomenon. It's just pure noise. I'm just adding to X a random vector of the size of X, that is 285 observations. I'm just as you can see, haven't done anything that relates X to the random noise. And now let's look again at the residuals and the sum of residuals. First, what I can look at is what is exactly actually the value of alpha. Now that I've added that new vector of noise, well, it seems that my vector of noise is taken into account. Okay, if you remember, so the value of X is very small, so I guess this is why it doesn't appear here. But it seems that let's put a few lines of this, a few columns, sorry. So those are my variables here. So this is probably the this is probably the age, maybe this is the surface, this is the distance, this is the constant, and this is just the noise. It's easy to spot the noise because it has values which are not rounded. Okay? So alpha actually gives a 0.3 coefficient to just pure noise to explain the rent. Okay? And now look at the residual sum of squares. It has gone down from 118 to 116. Okay? So here we have really a big problem with regression with least squares. We have an obvious problem, which is that by giving you a variable which was completely unrelated to the phenomenon, I'm improving my performance on that metric. I'm improving with respect to the least squares criteria. Okay? So if someone gives you a data set with 100 variables and adds a 101st variable, another variable, your least squares will always improve. You can only improve. But does it mean it's worth it? Well, here in this example, it's definitely not worth it, right? Because in terms of interpretation, you're basically using a variable that's complete noise to predict something. So it's a catastrophe in terms of inference. It has nothing to do with actually what's going on. So this is why Occam's razor, or the idea of regularization, tried to go away from this tendency of least squares. So on the one hand, we'll always have this trade-off. You want a good fit. You want f of xj to be close to yj. But if you go beyond a certain point, if you only look at that, it will drive you into some real problems. And those problems are called overfitting. So to counter this influence, we need another idea, which will insist on the fact that, okay, we want to have a good fit, but we don't want it to be too complicated. We don't want too many variables. And there's many formulations of this. So this is Occam's razor. I will give you a few ideas here. We have a few minutes left to talk about advanced regression techniques. But there is a huge literature on this. So the first things that we need is a few reminders on vector norms. So I've been discussing the Euclidean norm a lot of times, so I'm pretty sure you're familiar with this notation, but maybe you also know the Q norms. So the Q norm is the Euclidean norm, the Euclidean norm is the Q norm for Q equals 2. So when I write AQ here, it's just the sum of AI to the power Q power 1 divided by Q. So if you just replace Q by 2, you will see immediately that it matches. And in particular, there's a famous and important one norm, which is the 1 norm. And it's called also the Manhattan norm. It's just the sum of the absolute values of AI. And then there are other things that you can see. There's the infinite norm, which is the limit of this when Q goes to infinity. And there's the 0 norm, which is the limit of this when Q goes to 0. So the infinity norm is easy. It's just the maximal element over all the AIs. This one, the 0 norm, is very important. It's basically the number of i's such that the I is not equal to 0. Okay? So this is really important. The A0 norm is just the number of non-zero variables in that vector. So the first approach, which I think was proposed to tackle ill-posed problems and the fact that X transpose is not invertible, is something called Tikhonov regularization, or ridge regression in statistics. The idea is the following. You remember that we're trying hard to minimize L of alpha, and I told you that this can run into some overfitting issues. The approach proposed by Tikhonov is just to add to that minimizer a penalty, so lambda is a number, and alpha here is the Euclidean norm of alpha to the power 2. So instead of only minimizing L of alpha, we are going to minimize this quantity. And if you do that, incidentally, it's very easy that you can show that the actual minimizer from this alpha here becomes this alpha. What is the difference between here and here? Well, it's just simply that we've added an identity matrix here. So this matrix here we were discussing many times, and maybe it's not invertible, etc., etc. We know that it's positive definite. We know that we add an identity, a matrix proportional to identity here. So this becomes always now invertible. And in practice, what this changes is that if you do that, the condition number of this matrix is actually this one. So it's lambda max plus lambda min, but plus lambda on both sides. So usually this decreases a lot the condition number. So this is really important, but we don't have the time to go into details. It's more important to look at this. So this was a regularization approach to make the problem numerically more stable. But this is not enough. What we actually need is to do variable selection sometimes. If I give you 100 variables, you want to keep 5, which are enough to explain the rent. You don't want to include the distance to the convenience store, or that might be irrelevant actually information, or the distance to the poster, etc. You want to find a good set of variables. So suppose you fix the number of variables to p. I give you a data set, and I ask you, please, give me the best subset of 5 variables which explains this, the y. So this is just this problem. It's the minimum over alpha, over all alpha such that the 0 norm of alpha is p. Remember that the 0 norm is the number of non-zero coefficients. So if a vector alpha has a lot of 0 coefficients and only 5 non-zeros, it basically means that it's doing feature selection. Okay? If I have a big alpha here, which is just 0, 0, 0, 0, zeros, and here 3.5 and 4.1, okay, times my vector x, my matrix, data matrix x, it basically means that I'm just considering this line and this line, this variable and this variable. So this is exactly what we would like to solve if we follow Occam's razor. define a number of variables, and minimize. Unfortunately, this is very difficult to implement. Actually, in practice, if you really want to solve this exactly, you need to compute the residual sum of squares for all combinations of p variables in n variables. So if you have, let's say, 30 variables, I'm sorry, this should be d. If you have n or d 30 variables and you want 5 variables, then you need to run 150,000 regression problems. If I have 100 variables and I want to select the 5 best, it's impossible. It's completely intractable. I mean, I could use all the computers of all the planet for 1,000 years and it would still be impossible to compute that. So what do we do to get around this? Well, there are 3 approaches that I can give you. The first one is, I just want to check that I have, okay, that's good, because this clock is ahead. There are 3 ways, and 2 of them are really intuitive, and the third one is more advanced, but I like to mention it. So something called forward search is very popular. It's very simply a heuristic. It's a heuristic in the sense that the result that it will give you is not this. It's not the best alpha in that sense, but it kind of works. So people have used it quite a lot. So here is the intuition. It's a very simple idea. Suppose you start with variable number 0. Variable number 0 is just a constant, okay? So basically you're saying, I'm going to predict y by a constant. Usually you select the mean of the y's as that constant. But now you have a choice of 100 variables. So if you want to find 5 good variables, well, you say, okay, I'm going to add 1. Okay? So what you do is, suppose you are the kth iteration of this algorithm. So you've already selected k variables. If I have k variables, the question that you ask is, what is the most info variable that I could add to my set of variables? So suppose I have selected the rent, to predict the rent, I have selected the age and the surface, and I have 98 other variables. The question that I ask is, okay, if I want to have a third one, which one would it be? And so what you do is that you compute for each of those variables that you haven't selected yet, 0d that you haven't selected, basically the residual sum of squares that you would get by adding this variable. Okay? So it's very intuitive. I have 4 variables so far. I have 96 left. Which one is, of those 96, which one would be the one that would decrease the most my residual sum of squares? And you add it. Okay? And then you go on like this until you get 5 variables. So this is the outline of very simple algorithm. If you have understood forward search, you will understand backward search. Backward search is start with all the variables, and you ask the different question, which is, what is the least informative variable I could remove? So basically, you try to remove each of the variables that you have already, and then you see for which one does my sum of squares gets the least hurt, basically. I want to have a low residual sum of squares, but if I remove one, which is the one that allows me to remove, to lower it the least as possible? So this is backward search. So those are 2 heuristics which actually can be combined usually. It's very common to do forward, backward. So you would add 5 variables, remove 3, add 5 variables, remove 3, up to until you get the results that you want. Now the last one I can only describe in a few words now is lasso. So let me just introduce lasso this way. The naive least squares is just the minimum of L of alpha. L is your least squares criterion. The best fit with p variables, the idea of Occam's razor, is the minimum of alpha for alphas which only have a support of p non-zero variables. This is very hard. You have to trust me on this. I didn't prove anything. But this is very difficult to compute. You actually have to compute all possible combinations to be sure that you reach the minimum. Tikhonovly regularized z-squares is a way of regularizing your X transpose, so that it's invertible, so you avoid numerical problems, but you don't do variable selection. The last one, which is if you really look, it really looks like Tikhonov, but it's not. It's called lasso. And the idea is to minimize L of alpha, but this time you add the one norm of alpha. Okay? The Manhattan norm of alpha. If you do that, in some cases, you can actually recover exactly the minimum of this. But there are a lot of conditions to get the recovery of the good alpha. But a lot of people now are using lasso to do variable selection. Okay? So in this case, and in this case, you remember we had an explicit closed form solution for alpha. In this case, I cannot give you a solution for alpha. You have to run an algorithm, optimization algorithm. But when you get it, you will get a vector alpha, which is such that it has a lot of zeros and some non-zeros. Okay, so that finishes this lecture. So we'll talk about classification next week. Thank you. Any questions, maybe? Okay, thank you.